I heard that the whole no school on Monday thing is still tentative. If we get a blizzard tomorrow, then we still might have school Monday.
Oh my goodness.
Because it's still technically a snow day, and if we have to use it before Monday, we have to use it before Monday, something like that. So super fun. So I may or may not see you Monday. I'll probably see you Friday, not Monday. All right, then I think let me pull up the slides. We'll finish talking about gases today. We might start talking a little bit about phase change. We talked about energy, right? We talked about the Q equation. We did heat capacity of a metal, right? Then phase change is going to make a fair bit of sense. Where did my down there goes? Open up PowerPoint. Here we go. All right. So there's a couple things about gases that we want to finish up before we get to that. One of which is relevant to the problem. It has you calculate pressures separately, right? On one of the what is the pressure of each gas? Does it matter that we've got a bunch of different molecules added together? No, because as long as they're all the same temperature, they're also going to behave the same. So you can either calculate their pressures separately, or you can add them all together to get the total pressure. So that's what's called a partial pressure. And hang on. There we go. So I'm just continuing on from our slides the other day. No, I deleted those ones. Sorry, we'll get those in a second. In the meantime, let's do a practice with PV equals nRT. All right, we got 2-liter bottle sealed at sea level, room temperature. How many moles of gas are in the bottle? All right, well, you work on that. I'll bring up the slides on partial pressures. Hang on. What is equivalent to torque? So PSI, torque, ATM, they're all pressure. What's the exact same as torque though? What's torque another word for? Mercury, millimeters of mercury. Because millimeters of mercury doesn't really sound like a pressure unit, so they basically just redefined it as torque. Right, so on your equation sheet, all of those, you have that pressure section on your conversion sheet, right? So we've got 760 torr, 25 Celsius, 2 liters. Is there anything particularly tricky about this one other than you need to know what the variables mean, right? And then there's a lot of values for R. If you look up the ideal gas constant on Wikipedia, there's probably 100 different values for R that all just have, it's the same number, just in different units for all of them. So what you have to, so since we don't really want to have to look up a different value R for every, we could look up a different value of R that's in torr instead of in atmospheres, but then we'd have to memorize another number for no reason. So what we do instead with all these is we're just going to take everything and convert it to the units of torr that we're used, or the units of R that we're used to. So if I give you a pressure in PSI, just convert it to atmospheres. If I give you a temperature in Fahrenheit, convert it to Kelvin. If I give you a volume in gallons, convert it to liters. Just put everything in all your volumes. If we're talking about gases, you just want all your volumes in liters. You want all your pressures in atmospheres. You want all your temperatures in Kelvin. And then you can use the same value of R all the time. So 760 torr, if we want it in atmospheres, that's an easy conversion if you know the conversion, because what is it? It's 1 atmosphere. 760 torr is the definition of 1 atmosphere. So we just get 1 atmosphere. 25 Celsius is what in Kelvin? So add 273.15. And how many sig figs do we get to keep? Oh, just 2. This is one we got to watch out for. This was addition, not multiplication, right? So we keep the same uncertainty. We were plus or minus 1 on our Celsius. So our answer's got to be plus or minus 1. So we're going to keep it to the ones place. Right? So can't forget about those sig fig rules. Right? Almost all the time, you're just counting sig figs, right? Because mostly we do multiplication, division. This is one of those rare addition problems. Kelvin. And we're already in liters, so then we're just plugging in here. 1 atmosphere, 2.0 liters equals N times 0.08206. And I know it's a lot of extra writing, but again, I would highly encourage you to write your units on R just to remind yourself to make everything cancel out because you didn't forget to convert something. Landon? What's that? R is a constant. You're actually gonna measure R in lab tomorrow. You're gonna do a reaction. We'll do the practice problem with it in a second. Where you're gonna do a reaction where you can calculate how many moles you're gonna make. And if you know the atmospheric pressure and you know the temperature and you know the volume of the gas you make, you can actually calculate R yourself. But for now, R is a constant. It's always the same. 0.8206 liters, atmospheres over mole, Kelvin. And then times the temperature, 298. So N is 0.817. And where are we going to round that? Just 2. So 0.82. 0.082. Is R a measured number? I just told you you're going to measure it tomorrow, right? Yeah, it is a measured number. So if we added more digits to it, we could add more sig figs and make it more exact. So, but 4 sig figs is almost always going to be enough. So if you remember 0.08206, that's almost always good enough. We don't almost never need 5 sig figs. All right, so easy enough. It's just another algebra equation, right? Know the variables, know your units, and it's just a little bit of algebra. So let's practice The reaction that you're going to do tomorrow is you're going to take a reactive metal. We're going to take magnesium metal. We're going to let it react with hydrochloric acid. It's a known reaction, and it winds up being really useful because of this is a solid, this is aqueous. It's going to react to make aqueous magnesium chloride, and hydrogen gas. So we need to balance this, but the whole point of what you're going to do tomorrow is we're going to take this equation or this reaction. If we measure an amount of magnesium, we can use stoichiometry to figure out how many moles of hydrogen we're going to make. And if you look at this setup right here, this is basically just a long graduated cylinder that's closed at the end, kind of like the barometer. Basically going to put magnesium in the tube at the bottom, add some hydrochloric acid to the water, and if the tube is filled with water, when you generate hydrogen, it'll collect the gas at the top, and you can measure the volume of the gas. So you're going to get some number like volume is 20 milliliters. You're going to measure the temperature of the water and assume it's the same temperature as the gas. And we can say the temperature is 22 Celsius. And so if you know all of the pieces of this equation except for R, if we can measure the atmospheric pressure, we can measure the volume of the gas. If we can predict N by using stoichiometry. And then temperature is just temperature. We can measure the temperature. We can solve for R. R is just going to be equal to PV over NT. Well, since we have a way to predict all of these numbers, we'll be able to calculate R and see how close we can get.
Will R change if we're not at 1 atm?
No, as long as we put in the true pressure in here. So this is going to be another one like the gas laws lab from the other day, where we're going to have to measure the atmospheric pressure at the college and write it on the board, and everybody's just going to have the same value here. One of the things that will be different, though, is if we have this gas up here that's a mix, it's going to be hydrogen, and then we have water here. This is not actually just going to be pure hydrogen gas, though, right? Because there's going to be some water vapor mixed in. And so there's actually one more correction we do. And so we actually are going to have a mixture of two gases here. We only want to take into account the hydrogen gas, right? Because that's what we're predicting the moles of here. And so basically we just do a quick subtraction, because if our total pressure, P total, is equal to pressure of the hydrogen plus pressure of water, if we know what the vapor pressure of water is at any given temperature, we can just subtract it. So just the same way as the other day when we measured the syringe, and we said that the pressure, or we added the two pressures together in that case, right? We had atmospheric pressure plus the added pressure of the object we balanced on top. We just added them together. Here, we're just going to subtract the vapor pressure of the water, and there's just a table in your lab procedure that says, okay, at this temperature, this is your vapor pressure of water. And you just subtract that number of torr from the atmospheric pressure that day. All right. Did we talk about the Hindenburg in this class yet? Anybody know what the Hindenburg is? Big old blimp. What happened to the Hindenburg? Blew up. It was a radio tower. No satellites yet. I want to say this is right around the same time as the Titanic, but it might have even been a little earlier. It was filled with hydrogen. They were trying to make it float as well as possible. So now if we want to make something float in the air, we use helium, right? It's actually even dumber than that. They had helium, except that helium weighs more than hydrogen does. So they couldn't get it to float as well. And it was cheaper to make hydrogen. So they filled it with hydrogen instead. Hydrogen balloons float even better than helium balloons. However, hydrogen's highly explosive. And so when it got too close to the radio tower, I think the radio tower had scratched a tear in the side of the blimp and caused a spark, and the whole thing just went up. And actually, in the whole thing, it was one of the first cases of like a national disaster, a worldwide disaster being like broadcast while it was happening, because this is one of the first times that a big disaster had happened since radio had been invented. And so they were broadcasting this event like, oh, Hindenburg's coming to town. We're on the radio. We're talking to everybody about it. And so while this is happening, while the blimp is blowing up, it's being broadcast live on the air. Just on radio. They didn't have television at the time. But if you ever heard the phrase, oh, the humanity, yeah, that comes from that broadcast. That's what the radio telecaster was saying, talking about the horrible loss of life that was happening. No, that's the wrong one too. Hang on, there's pictures of it too, because it actually was not like an all at once explosion. It was more like a kind of a slow moving fire in the middle of the air. And it's actually, the loss of life wasn't, we looked this up last year, I think, was it 30 or 50 people in the Hindenburg? Double digits, but it wasn't as many as you would think for how large of a structure it was. Yeah, that was part of the whole point, was that it was supposed to be like the better way. Passenger planes weren't really a thing yet. And so if you wanted to go from one place to another, it was like you took a boat or you took a blimp. And so blimps were like new and sort of very luxurious.
35 people on the airship.
Where the heck did that just go? I just had it. Oh, that's why. Okay, hang on. This one. Oh, you know what? It wasn't even a radio tower. It was how it docks. Like when you pull a boat up to a marina, you have to pull it up to the dock, right? So you can get on and off. There was a tower where they would dock, and then people would climb off. They would hold it in place for the people to get off. And the pilot got too close to the tower. All right. So, how many moles of hydrogen were in the Hindenburg? A lot. We can calculate it though. So, first things first, though, we have to define some terms. There's an easy way to do this. And we're going to use what's called standard temperature and pressure to do this. So, which is abbreviated STP, like the oil company, like the post-grunge band. if we know that certain things are going to be a constant, like the atmospheric pressure doesn't change that much day to day, especially if we live within, say 100 miles of the ocean, like most of the population of the world. Most of the population of the world, and by I say most, I mean like 90% lives within about 500 feet of sea level, which means that almost everybody around the world has the same atmospheric pressure. We're the exceptions up here in the mountains, right? So that's why they defined it as 1 atmosphere. And then they said standard temperature, they defined it as 0 Celsius. Why would that make sense? We're talking about gases. Is that our average temperature that we're used to dealing with? Not indoors, but at least before climate change really caught cooking, that was actually a pretty good estimate for the average atmospheric temperature year round. If you average out year round the atmospheric temperature of the entire world, it's about 0 Celsius. So what's that? They measured it. They had the they were measuring at different latitudes in different places, and they just averaged everything out over time. You measure the air temperature outside. I'm sure that there's more statistics behind it to make sure that they did that, but that was just a good estimate for what the average air temperature was. It's still not actually that far, but air temperature hasn't changed that much due to global warming yet. I want to say we're about 1 Celsius on average. Again, average for the entire year. But if you're going to pick one temperature for a gas and you're dealing with things that are outdoors, 0 Celsius is a convenient number. Plus, it also makes the conversion to Kelvin really easy too, right? So, how many liters of gas correspond to 1 mole of gas at 1 atmosphere pressure and 0 Celsius? So basically, we know everything except for volume. We're going to use standard pressure, standard temperature. If we want to know the volume of 1 mole of gas, we're just going to plug 1 in for N. Solve for volume. So volume is equal to nRT over P. Once we plug in all our numbers, 1 mole, 0.08206 liters, atmospheres, mole Kelvin, 273.15 Kelvin over 1 atmosphere. We get 22 liters. Unless we plug something in wrong, this is the answer we should get. This winds up being a pretty useful number to know because it allows us to actually relate liters of a gas directly to how many moles it is, as long as we're at standard temperature and pressure. If we're at STP, we actually have a really straightforward conversion. We can say 22.414 liters equals 1 mole of gas at STP.
Wait, so we use that like a constant, like you're going to take like a T squared, something like that, to go from 22.41 liters to 1 mole gas.
As long as you're at STP. So that actually makes that Hindenburg problem relatively easy to solve if we assume we're at STP. Now it's just a conversion problem, right? Basically, all this 22.414 liters, all that does is it basically has PV equals nRT built into it for a set temperature and pressure. And since most things, for the most part, we don't differ that much from 1 atmospheric pressure, we're at about 80% of an atmosphere here. And most temperatures in Kelvin aren't off by that much from 273. It's also a good number to just have in the back of your head. If I make a mole, if I do a calculation and I'm going to make a mole of gas, that's going to be about 20 liters of gas that I make. So you have to be prepared for that. One example of where that might have been useful. Did anybody do the baking soda and vinegar volcano as a kid?
Oh yeah.
If you'd been able to predict just how many liters of foam you were going to make, that would have been really helpful for your parents for not making a huge mess everywhere, right? Did anybody else overestimate how much or underestimate how much gas it was going to make a huge mess all over the floor? Or was that just me? Right? You can actually predict that ahead of time if you know this. If I put 100 grams of baking soda, if I put a box of baking soda into the vinegar, that's going to make 100 grams is about the molecular weight of baking soda, I want to say. So that's going to make about 20 liters of gas. If you visualize with 20 liters, look, 22 liter bottles or 10 2-liter bottles of foam that you're making, right? So you have to be prepared for that. Although making the mess part of the fun of that experiment, isn't it? All right. So how are we going to calculate this? We've got this fun new conversion we can use. We've got cubic feet, 5 times 10 to the 6 cubic feet, 5 million cubic feet. How we get that to liters so that we can get to moles? Inches to centimeters, centimeters to liters. We just got to remember to cube everything, right? Everybody remembers how to do this? 1 foot, 12 inches, cube it. 1 inch, 2.54 centimeters. Cube the whole thing. Then we can do 10 to the 3 centimeters cubed is 1 liter. Do we need to cube that one? Why did we have to cube this one? Because this conversion was feet to inches and we were in cubic feet. If we cubed this one, we'd get centimeters to the 9th. We don't want that. Centimeters to the 9th doesn't even make any sense. Right? What is it? What is a cubic liter? A liter is already a volume, right? A cubed volume doesn't make any sense. So we're not going to cube this one. And then we can get 1 liter, 22.414 liters. So think back to right before the midterms. If I told you that this conversion was going to be the easiest part of the lecture of the day, you would have looked at me like I was crazy, right? Think about how far you've come in this class. Even if you still feel like you're struggling a little bit, this should make sense, or at least seem familiar, because you put in that work. I just like to periodically remind my students, even if you're still struggling, you've come a long way. So then we plug it in. That's going to be like 1,000. So we're at 10 to the 9, 5 times 10 to the 9, probably more like 10 to the 1 times 10 to the 10 times another 10, 1 times 10 to the 11 divided by 1,000. Now we're at 1 times 10 to the 8 divided by 20. Gonna get 10 to the 5 times 10 to the 6. We come back to 5 times 10 to the 6. Did it wind up canceling? No, that can't be right. Cancel out down. No, it's gonna be like 2 times 10 to the 6, huh? It's pretty close to the same number, actually. Coincidentally. What do we get when you plug it all in?
Yeah, 6.3 times 10 to the 6.
6.3 times 10 to the 6. So it's just coincidence that this one wound up being close to the same because cubic feet and all that conversion wound up working out. That's a lot of moles. It's a lot of gas molecules. You take a little bit more, science will be able to do things like, well, this reaction produces this much energy. How many kilojoules of energy are produced from this process? And then we could actually work backwards and calculate some interesting things that way. All right, so everybody feeling okay about PV equals nRT? It's just one more way to get to moles. And now we even have a shortcut. If we're at STP, it's even easier. And again, the way that this might show up in the exam be, so there's another familiar stoichiometry problem, right? Just with concentrations. The next one is a pH problem. Oh, where is it? Did I pull it? Maybe I made the test easier than I thought I did. There it is. Gas loss. Gas burns. Basically, if you have a, oh, I did make this one a little trickier than I intended to. If I recall, not that many people did very well on this one. So it looks very similar to one of your problems from yesterday, though, right? What's your final pressure after the reaction happens? Figure out your total gas moles, and then figure out your final pressure using PV equals nRT, right? So it's stoichiometry, and then you just take your moles at the end and throw it into PV equals nRT. Almost always for gases, you're going to wind up coming back to PV equals nRT, because for the most part, under standard Earth-like conditions, the assumptions that we make in the ideal gas law wind up holding up. Let me go back to the. All right. Oh, there's the next part with the energy. The reaction releases 285.8 kilojoules per mole of hydrogen. How much energy was released when the Hindenburg exploded? That's not going to be that much trickier, though, right? We've already got it in moles of hydrogen. It's just one more step. Remember, kilojoules per mole is just another conversion, right? Then 6.3. We have a number that's for every 1 mole hydrogen, 285.8 kilojoules of energy released. So that would give us a number in kilojoules, give us something like 1 billion kilojoules. Probably put it in, kilojoules per mole is kilojoules is a really common energy unit, more so than just joules. We'd actually probably put it in megajoules at that point, just because we don't want it to be too large of a number. But basically, it winds up being something it's a large number, but it's still about 1 million, no, 100 million times smaller than the Hiroshima bomb. So it seems like a lot of energy. It was a huge disaster, killed 37 people. but it's actually a pretty small amount of energy when we're talking about things on the order of nuclear weapons.
Very cool.
In fact, we could actually put it in kilotons of TNT if we wanted to. All right. To go back to where I was headed before I saw this slide and got distracted. Does anybody know why they call it the ideal gas law? Because it's ideal. That's what I always thought. It seems like it's a pretty useful equation, right? It turns out it's not the equation, it's not the ideal gas law, it's not the law that's ideal, it's the gas we're assuming is ideal. And an ideal gas, we're basically assuming two things that make PV equals nRT work. And the two things we're assuming are that, well, one of them we already touched on today. We are assuming that all gas molecules behave the same way, right? That's why we can just add together the different pressures or the total number of moles, and it doesn't matter what they are. It turns out that that actually has two different assumptions built into it. What's one thing that can be different about different gas molecules? What if I said we've got a mole of nitrogen versus a mole of hydrogen, what might be different? The masses are going to be, the gas molecules are just straight up a different size, right? So by assuming that all of them are the same, we're actually making the assumption that the gas molecules themselves have no volume. Right, so the two assumptions. So, and they're kind of built into those derivations that we used. So gas molecules have zero volume. And under normal circumstances, that's a decent assumption. Gas molecules are really, really small, right? When you calculate how many grams of CO2 are in a 2-liter bottle that you filled with CO2, it's a pretty tiny amount. It's mostly empty space. Where that assumption falls apart is if we start getting lots and lots of gas molecules into a very small space, you wind up with them actually being a significant portion of the total volume of the container is taken up by the gas molecules themselves. So let's think about this classroom as being the container for a bunch of gas, and every person in this classroom is a gas molecule. If we want to know the total amount of empty space in this classroom, does it matter that we're in this classroom? Are we taking up space that would otherwise be empty?
Yes.
Yeah. Think about if we blow this room up to the size of, I don't know, the entire lake, all of South Lake Tahoe, or all of Lake Tahoe, and all of us jumped in the lake. Are we really taking up that much space in the lake within sig figs? No, it's only when we all get confined into a smaller space that we actually wind up taking up a measurable amount of that volume. Right, so for the most part, this is a decent assumption. The other assumption is that gas molecules don't interact with each other or with the container itself. Because we're making the assumption these gas molecules are flying around at random and they're behaving like they have perfectly elastic collisions with the containers or with each other. So we're basically assuming that they're going to behave like pool balls on a pool table. When pool balls hit each other, for the most part, there's no like sticking happening, right? They bounce off and the total amount of energy winds up being conserved pretty well. But what if we replace those with, I don't know, what's something sticky? What if we covered those pool balls with glue and then had them run into each other? They're not going to retain the same amount of energy that they had before, right? Then when they run into each other, they're going to stick, and that's going to slow things down. And if you slow down those those gas molecules, you're affecting the total pressure of that system. Right, and plus we're also assuming that also assumes no phase changes. We're going to talk about phase changes next week or on Friday. But basically we're assuming that our ideal gas stays as a gas. No matter how hot or cold you get it, it will never turn into a liquid because it has no interactions causing those molecules to stick together. There's actually a version of PV equals nRT where that actually corrects for these, but it makes the math way more difficult, and still is fairly limited. So this version of the equation is called van der Waals equation. And van der Waals equation basically just has two corrective terms added into PV equals nRT. So van der Waals equation, it still looks more or less like PV equals nRT. It's going to be pressure plus a correction term. And then it's volume minus a correction term equals nRT. So A and B are new variables, but N is the same N we've been working with. N is moles. Volume, V is still volume. You can see that, so it doesn't look that bad to solve, but what if I asked you to solve for moles? Now all of a sudden we've got a squared term, we've got to FOIL this whole thing. It starts looking really nasty to try and solve this algebraically if I ask you to solve for either volume or moles. That'd be something you'd want to use a solver for. Pressure is not too bad to solve for. Temperature is not too bad to solve for, but moles and volume are a huge mess. We can actually kind of see what these this version of the equation actually has. You can kind of see these two assumptions being corrected for. This B term, A and B are actually both just going to be constants. For every gas is going to have its own A and B van der Waals constants. Basically, B is the volume that the gas molecules do take up. So the units on B are literally liters over moles. So if you had a mole of that gas, not as a gas, how much space would it take up? So then you just take that and you multiply by moles and you'll get liters. And so basically your effective volume is slightly smaller than it actually is because the gas molecules themselves take up space. This one's a little bit harder to see. The units on A are kind of weird, but it has to do with the squared term is, so moles over volume is concentration units, right? And basically what this is okay, so if you have a concentration of gas molecules in a space, this has to do with the probability that they run into each other. And then if they run into each other, what happens? A is basically how much do they stick when they run into each other. And even this, as complicated as this looks, this still only works if you have one pure gas. If you have a mixture of gases, you can't do this because let's say we had a mixture of hydrogen and nitrogen. A nitrogen molecule could run into another nitrogen, is going to have one A value. But if a nitrogen runs into a hydrogen, that's a different A value. And if a hydrogen runs into a hydrogen, that's a third A value. So we would actually have to have a much larger term just for a mixture of two gases. You had 3 gases, now we have 9 different ways they could run into each other, right? Not 9, you wind up with, what, 6 without duplicating? So basically this equation winds up not being very useful. If you really want a lot of sig figs and you're dealing with certain cases like a pure gas at really high concentrations or really high pressures, you wind up with these two assumptions aren't good assumptions anymore. Right? As soon as you have a really small volume or a really large number of moles, these two correction terms wind up getting really big because the odds the molecules hit each other are big. Or they're actually taking up a measurable amount of your container. But under normal Earth-like conditions, these two correction terms are almost zero for everything. So for the most part, PV equals nRT is good. The whole point of this, I may ask you on a take-home problem on one of the take-home problems of the test to solve this. It won't be for moles or volume. And I won't ask you to do it on the timed part of the test because for the most part, it just doesn't matter. But what I do want you to know is that your ideal gas law makes these two assumptions. You don't need to necessarily know how to fix the ideal gas law, but you should know when it's going to fail. And it's going to fail when these two assumptions aren't good anymore. When you've got a really small volume with lots of gas molecules in it. And also, if you get to a point where you have a phase change, right? A phase change happens because the attractive forces between molecules are greater than the force of the kinetic energy of those molecules bouncing around on their own. So in our pool ball analogy, if you put enough glue on the pool balls so that when they ran into each other, they didn't like bounce off but slightly slower, they just stuck. If you have enough of those stick together, all of a sudden you don't have a gas anymore, you have a liquid or a solid. Right? So we're making the assumption that not only when we say the molecules do not interact, they also won't go through a phase change. So basically you can't use the ideal gas law for water vapor if you're close to 100 Celsius, because at 100 Celsius, it should be condensing, turning back into a liquid, right? Other things start happening. That said, 9 times out of 10, if you have to do a calculation involving gases, it's going to be PV equals nRT. All right, we've got 15 minutes left. So here's a list. Here's van der Waals constants for some common gases. And you see, basically, you would just have to go through and look these up if we wanted to actually do one of these calculations. So let's see. Let's just prove to ourselves that this is going to be a useless calculation. Not on the in-class file, maybe on the take-home part.
Wait, what's it going to be divvied up into? How much take-home questions do people have?
So it'll be 10 in-class questions again, just like the midterm. And then there'll be 2 questions that'll be 10 points apiece that'll be take-home. That's the point. Is it's one way to make sure you get yourself points. The other way you can use that is if you know that you've done a really good job turning in all your work, and you have a high A in this class, and you did okay on the midterm, you might not really need to do the take-home. Or at the very least, you can basically write off 2 questions on the in-class part. If you do the take-home and put in the work, you can take a 0 in 2 different parts of the final, right? And still get the same score overall. And that's the sort of thing that I would do as a student. It's not what I would necessarily recommend that all of you do. But if you're sitting, there's no difference in your LTCC grade between getting a 98 and getting an 89.5. LTCC doesn't even do pluses or minuses, right? So an A is an A, whether it's a 99, and usually, yes, I usually round up at about 89.5. But aim for 90. That's your safety margin. Don't aim for 89.5. Don't make that mistake like I did when I was a student.
It'll only go in the categories, correct? And
it'll go into the exam category. All right. I still wake up in a cold sweat every now and again because of my trig pre-cal final. I was a terrible student when I was in high school, and I decided, not consciously, it was a subconscious decision. I was going to see how long I could go into the semester before I turned in any work and still get an A in the class. And it turns out right around midterm was for that class. So I had to get a 98.5 on the final exam to get an A in the class.
Oh, did you get it?
I got a 99. But I was really nervous. So don't do that. Plan for a little bit of a margin of error. That's because pre-calc is really straightforward if you understand the rules. All right, how do we? So if we have 1 mole of water at 22.414 liters at 0 Celsius, what should our pressure be? 22.414 was very strategically chosen. That's our standard pressure. That's our volume at STP, right? So what is the pressure then in this system if we use ideal gas law? 1 atmosphere. So let's plug it in with the van der Waals equation to see how far off of 1 atmosphere we are. Spoiler alert, not very much. It's going to be really close to 1 atmosphere. So we're solving for P. A for water is 5.46. And just in the interest of space, I'm not going to write the units for this one because this is not, because we need to conserve space on the board here. N squared over V squared. 1 mole over 22.414 squared. Volume is 22.414. Moles is 1. B is for water 0.0305. Equals 1 mole times R times 273.15. One over 20 is going to be about 0.05 squared. So this number actually is just going to come out to be 22.414 again on that side. What is 22.414 minus 0.031? 0.383 what? My brain's a little tired. I'm not able to borrow in my head right now. What do we get for this number? Just do that subtraction. 414 minus 0.0305. 389. $384. Thank you. And what do we wind up for this term when we calculate everything in? $5.46 times 1 over 22.414 squared. 0.01. 0.0109. once we actually start doing some of the arithmetic, it's just a bunch of number crunching, simplifying to get to this point. Divide both sides by 22.384. And then subtract 0.0109. I get pressure equals 0.9904. And I'm not really paying that much attention to sig figs right now because the whole point is just that that's still really close to 1, right? For the amount of extra work we had to get there, especially considering we can't even solve for moles anymore. That's just straight up more trouble than it's worth for the most part. Under normal atmospheric conditions, anything close to Earth-like conditions. Basically, anytime your pressure, if your pressure is under about 100 atmospheres, you're not going to use this equation. When you get past that, if we're starting, and now we're starting to talk about astronomy. If you're talking, or planetary sciences, if we're talking about the surface of Venus, you might have to use this equation. Or make some other approximations in there. It's not going to be enough to just use PV equals nRT because the conditions are so different than what we're used to on Earth. All right. Is there anything else I wanted to go over about gases before we move on? Vapor pressure we talked about a little bit. Effusion's not all that useful. How much time do we have?
Yeah, 10. Yeah, like
all right, let's spend the time on your assignment from yesterday. We could add a new question involving geometry and spheres, but we don't need to do that right now. If you want the tricky math problem, you can do that.